Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So today we have Yura Perov visiting us for the day. Yura is about to finish his undergraduate degree at the Siberian Federal University. He spent 1 year at MIT working with Vikash Mansinghka and Josh Tenenbaum. And since October, he's been working with Frank Wood at Oxford. And he'll be starting his PhD this year, if I'm correct. And he's here to talk to us about probabilistic programming languages.
Good morning. So I'm going to go through generative probabilistic programming, applications, and new ideas. And the structure of my presentation will be as follows. Firstly, I will describe briefly about probabilistic programming. Then I will show you a few examples of generative probabilistic graphics programming. Then I will describe briefly some advancing techniques for better inference for probabilistic programs. And then I will touch briefly what I'm the most exciting point of my talk is automatic programming using probabilistic programming languages. And how I like to describe probabilistic programming is, first of all, it's compact compositional representation of your probabilistic models. So this is picture, I think, familiar for all of you. It's latent differential allocation model. And for humans, it's very easy to present the model in this way. So if you look to it, you understand what it is. It's the same representation of this model. And it's handwritten sampler, written in C++. It's about 300 lines of code. And you can actually make inference in LDA using this representation of this model. And this is third representation of the same model, LDA. And it's about 10 lines of code to describe the model. And then you have observations, as many as you have words in your data. And you can see that probabilistic programming gives you opportunity to write in compact way your model and using different inference techniques. I'm sorry. For example, meta-post-Hasten algorithm, sequential Monte Carlo and PMCMC, variational inference, and other techniques, via general purpose techniques, make inference in your models. And this is church-like languages. MIT, Church, Bear, Venture, paper hopefully will come very soon. Sequential Monte Carlo and PMCMC is being developed at Oxford by Frank Wood's group. And I will briefly touch how inference happens in church-like languages using meta-post-Hasten algorithm. So imagine that you have your model. Imagine that you have some Bayesian network model, the easiest thing you can describe in Turing complete church language. You have node MVS, which is sampled from prior, from categorical 0.1, 0.9. And then you have node VMCH, which depends on MVS. And if MVS is equal to 0, you sample MVCH from categorical. And if MVS is equal to 1, you sample from another categorical with another parameters. And then you describe the whole Bayesian network in this way. And then to make inference in this model, imagine that you have some last nodes in your model fixed. So you have some observations from your data. How you can make inference described in church paper. You sample, first of all, your model. So you make forward evaluation. You sample from prior. Then you remember all random choices you have to your random DB. And then you select, for example, uniformly randomly or using other scheme some random choice. You make local perturbation on it, using some local kernel. And then you rerun the whole program, reusing all random choices whenever possible, getting them from your random DB. And then either accept or reject this small perturbation of this node by calculating your MH acceptance ratio, where you have the probability of all state of all execution of your program, your new log score of your new execution of your program, and transition kernel, which in this case will be, if we pick up nodes uniformly randomly, 1 divided by number of random choices in your all random DB, the local proposal on your node, and potentially new randomness you create in your program. But because this is a fixed structure, you don't create any randomness. But potentially you can, if your generative model has, for example, at predicate flip Bernoulli, stochastic Bernoulli random variable, and you either have one stochastic procedures in consequent or other stochastic procedures in alternative, and you will create and remove your randomness. Does this make sense? And hopefully you converge from prior to posterior if you don't have edge cases, if it's ergodic and smooth enough.
Question?
Yes?
So in the case where you are flipping a predicate and new random variables are introduced, how do you sample the values of those new random variables?
There are different approaches, and the easiest one, you just sample it from its prior. It's the easiest way you can do, and it will work. It's not the best thing you can do.
Okay.
But it will work. And I agree that it's not the best thing. Okay, so this is another example of model you could write in Venture. I don't know how familiar you are with, I think, first of all, you are familiar much with probabilistic programming. I don't know how familiar with church-like languages and Venture. Should I show this example? Okay, so here you see CRP mixture demo written in church-like language. Okay, sorry, one moment. Sorry. Okay, one moment. I'm sorry. Okay, great. So here you don't have any points yet, and we have two-dimensional CRP mixture demo. So first of all, we describe our model. So we have some alpha hyperparameter, which is sample, for example, from uniform continuous. Then we have our cluster CRP process. We create new Chinese restaurant process with this parameter alpha hyperparameter. And then we have 3 lambda procedures. First is you get cluster mean, depending on the cluster ID and dimension. Then you have cluster variance, again depending on the cluster ID and dimension, 1 or 2. And then you get cluster for your point ID. And because we don't have any points, we don't have any data, and we just describe the generative model. And if you put point here, you first of all sample for this point number 0, its cluster. And then you sample a mean and variance for this cluster. But this predicts adjust for you. So if you run this program and get to what cluster this point relates to. And the main thing is that you have 2 observations. So you observe that your cluster mean of the point number 0 with the cluster it relates to and dimension 1, and this with variance for point number 0 with for cluster it relates to for dimension 1, it's equal to minus 5.25. So this is x coordinate of this point. And you define the y coordinate in the same way, and you add some noise using normal. So it's classical CRP mixture demo with some noise. And if you define a few other points, you have all your observations defined as probabilistic programming code. So you define your model, and then you add observations, and you see in real time how inference converges to your clusters. And here I describe not very interesting model. Sorry, not interesting data, but does this make sense?
And the line is your random?
This one? This is scale parameter. I just omitted it when I described the model. But the idea is when you have your variance, you have your variance distributed by beta and multiplied by some scale. because you don't know how large your cluster will be, you have additional uncertainty on it, and you can see scale. And scale as well helps you to find your solution. By this I mean.
So that's inferred.
Sorry?
That's inferred.
Yeah, this is from posterior. Yes. Okay. And now I'm going to application. So this is one example of generative probabilistic programming in graphics. It's SNP's paper, which was at the SNPs 2013. And I will show you how you can easily write your generative models and apply it in different applications, in this case in Vision. And this is joint work with Vikash Mansinghka and Tejas Kulkarni, who are main authors of this paper, and with Joshua Tenenbaum. And the idea is that computer vision is a pretty developed field. It's for many years, much work done in this field. And there are efficient bottom-up approaches, for example, feature extraction, segmentation. But there are limitations of bottom-up approaches in vision. For example, they require large training corpuses, as well as label training data for many approaches and bottom-up techniques for vision. They're difficult to build, including the software engineering aspect, and they're difficult to modify. They require a lot of feature engineering. They're clumsy in the variability. If you have, let's say, one captcha, it's easy to come up with some bottom-up approach, but the more variability you have, in general, it's harder to consider all possible things. You can, of course, use some features, but in general, current optical recognition systems which use bottom-up approaches don't solve captures, don't recognize captures. And the question is, for humans, it's easy to understand what happens here if we think that there is some blur, and most probably all of you can read that it's 1 for 0 point, maybe beware or freeware. But for optical recognition system, it's also hard to do it. And humans are able to process almost all of this kind of captures because we generalize beyond glyphs which we haven't captured. And does this make sense what I just described? And here we developed a framework of generative probabilistic graphics programming. So you do it top-bottom. You have your stochastic scene generator, where you sample your scene objects. For example, you sample object 1, x coordinate from some distribution, and you also sample control variables. Then you have approximate renderer, which you feed your information about your scene parameters and control variables. So you generate, you stochastically render something, your image, and then you have stochastic comparison, and you have data from the real world. You have your generated image from your approximate renderer, and then you're interested to consider this term in order to find this distribution. What control variables and what scene parameters describe in the best way this data you have from the real world. So one way to do the stochastic comparison, the simplest one we tried for CAPTCHA example, is for each pixel you put normal distribution, and you have your pixel from your generated image, for example, coordinate 5, x5, y7. You get red channel, you get noise, and then you observe it to the pixel you have from the real world image. So this is the simplest way you can do your stochastic comparison. And components of generative probabilistic graphics programming are 4. It's probabilistic programming itself, it's automatic inference, which probabilistic programming framework provide you. This is a Bayesian, approximate Bayesian computation, and computer graphics approaches like we don't propose, because we used renderers, we can get benefits of bottom-up techniques, as we did in our second example I will show you. So when you generate your image, at the end you can use different things, for example, reduce number of colors you have in your image. And first example is CAPTCHA. And this is a generative model for CAPTCHA. And you can see that here we define number of glyphs you have in your letters you have in your CAPTCHA. For each letter we define if it's present or not with Bernoulli distribution 0.5. We define for each letter position X, position Y, its sizes, if it's rotated or not, and how it's rotated from uniform continuous distribution. What letter ID it will be, English alphabet plus 10 numbers. We define blur, we define noise. Then we do some software engineering things to initialize the renderer. Then we render approximately our letters we have from the model. And then we do the stochastic comparison. And we use 90% of our inference time Metropolis-Haskell algorithm and 10 times with Gibbs inference for this model. Does this make sense? And here you can see, this is your real-world data, your input CAPTCHA. And here you can see how it's converged from prior to posterior. And this is speed up.
You mentioned 10% Gibbs steps, but in this complex rendering model, how would you do an exact Gibbs step? That seems to me, if you have something like a blur, it affects many variables at once, and you have to discretize or somehow approximate the Gibbs step.
The question is great. The Gibbs step in this case were applied only to discrete variables. And in this case, in this model, it was applied to the glyphs, what letters ID are. You're right. There is ways to make, for example, discretization, but we just make Gibbs for, because, I mean, Gibbs were exactly necessary for glyphs, and it's solved.
Can you say something about how long it's taken to find that solution?
Depending currently on the, it's about 30 minutes.
Sorry?
30 minutes. 30 minutes. So this is speed up much. And though probabilistic programming is convenient and a way to represent your models, now it's tremendously slow. For example, there is a digital allocation model we tried in church-like language with Metropolis-Haskell, and its asymptotics is the same if you write your handwritten stapler. But because of you interpret your model, instead of just you had compiled your handwritten sampler, it's now about 1,000 slower. And there is much work to do for this.
For this particular example, did you use some kind of annealing or parallel tempering or some other kind of things to make it mix?
No, but I see your question, and okay, I will go to the slide and have the slide special for this. So these are captures we solved, and you can look more carefully to the paper. And this again, inference. So answering your question, we don't have annealing as it is, but what we have Bayesian relaxation. So we have a few control variables for our in our model. We have blur on each letter. We have global blur, and we have blur on our data from the real world. As well, we have epsilon parameter, our noise, which comes from also some stochastic distribution. It's not fixed. And you can see that if we have this, it converges. And if we don't have it, if we don't have this, if we don't have distributions or our control variables, and if we don't make inference over them, it doesn't converge reliably. And you can see what happens here. You have your blur, and you have your iterations. You can see that, firstly, the blur increases for your letters, and then when it found its locations, it starts to decrease. So what really happens? I mean, as if you're a person, if you look to the problem, you firstly look from global perspective, and then when you solved it from global perspective, you make more precise look and solve the details. And it's the same you see here. Is it answer to your question? And another problem is road example, where it's a standard Kitty data set, and the problem here is to find the road, the left of road and right of road, and lanes to locate them on each frame. And here we use the same framework. So we have our stochastic renderer. We used again graphics engine with latent variables. I will show you the model soon. And the scene was represented in the 3D environment. So we just have stochastic coordinates of this 2D plane in 3D box. And then we had camera, and we rendered the image, and we received the road as 2D image. And this is a model. So we have road width, road height. We have position of lanes. We again have epsilon as noise, though here it works in a bit different way. I will explain how. We have our software engineering things to connect our renderer. Then we have one train example, data from one train example, and we draw our road to the 2D image, to surfaces, and then we observe, have stochastic comparison of our drawn image with our real world image. And these are samples from geometrical prior. Does this make sense? So this is.
Are you really just sampling from the prior, or is there some important sampling based on some preliminary use of the data to make the sampling from the prior more efficient?
This is just sampling from geometrical prior, and if I understand your question correctly, I have this slide. So we have train image, and from train image we locate where our left of road is, right of road, the road itself and lanes, and for each region of 4 we create color histogram of 20 colors. Colors we reduced using k-means, and this is sample from the model itself based on one train image. Does this make sense?
I'm not sure.
Okay, so
you do all this before you sample all this. I'm not quite sure what this.
Okay,
is.
I will explain in steps. Okay, yeah, sorry.
Yeah.
So we have our image. First of all, we reduced colors to 20 using k-means. For train image, we locate left of road, right of road, the road itself, and 3 lanes. So we select regions, and we receive color histograms of each of 4 regions. And this is in the model. This is what these setters are. Does this make sense?
So you use one training example to get your color histogram?
Yes. Yes.
But the geometry prior is fixed by hand?
No. I mean, this is a generative model. So when you sample from this model, you first sample your generative geometrical prior, and you can see how generative model is described. First, you sample your geometrical prior, and then you.
My question is, you hand wrote that part, right? You hand wrote the part that generated the geometry, the scene.
I mean, in terms of image, all happens here.
Geometry, did you write the first 6 lines of the program manually, or did you somehow fit them from data?
Oh, manually, yeah, sorry, manually. And first we sample, first part of the program samples from geometrical prior, and then it's samples from color histogram, and you receive the image like this. And we do the same thing for our test images. We reduce number of colors, and then we compare our histograms we have for each from our train image and from our test image, and we try to, inference process tries to match color histograms of test image to be as much as possible closer to color histograms of train image, and by this it finds the location of left of road, right of road, and other regions. Does this make sense?
So you don't have any important sampling. There's no important sampling of the geometry. So in other words, you have to generate a lot of samples of roads that don't even nearly fit the data before happily you generate some samples which are reasonably close to the data.
Roughly speaking, yes.
But you're not using rejection sampling, right? You're using metropolis.
Yes. So, I mean, we use ABC, and any sample from prior is appropriate. So, I mean, by this I mean it will not be rejected. It just will have some log likelihood. And the higher log likelihood, the more probability the next step will be accepted, and you do this random walk. And I agree that there are other different techniques which as well could be implemented in general purpose probabilistic programming framework.
If you have the likelihood, why do you use ABC? Oh, that's the next slide probably, but
He has render in there, right?
I just think it's a likelihood.
Of the observed variables.
No.
Carry on.
Is it not?
Is it clear? Should I
Do carry on.
Yeah.
Okay, and these are results. And you can see that we compared this with one of bottom-up approach et al. 2008, and it requires many parameters to be set before, about 90 parameters, and it's big amount of code, about 10,000 lines of code, while our approach is a few lines of probabilistic programming code and some render things, like can-mean algorithm and other things, which at most 1,000 lines of code. And you can see that with one train image we receive accuracy close to this approach, and with 15 train images and using maximum log likelihood approach, we receive better accuracy.
Is there a particular reason why you couldn't include the histograms as part of the probabilistic program and just learn them as well?
Sorry, I don't understand the question.
Well, you seem to be fitting the color histogram sort of as a separate process, not within the probabilistic program, right? You're sort of doing this maximum likelihood separately.
Yes, yeah, yes.
Is there a reason why you couldn't do it as part of the probabilistic program?
I think there is no reason and it's possible to do. I cannot come up very quickly, but I don't see any reasons why I can't, yeah. Maybe we just try to make the model as simple as possible to show that you can write it in a very simple way. But yeah, it's possible, I think, to make it.
Would the search space explode if you had the ability to curve the road?
Sorry, could you repeat your question?
So right now you're fitting a straight road all the time, but a lot of the frames actually have a road that curves to one side. Would that be infeasible to have in your model? Would it be too many geometric?
It's possible. I mean, maybe it would be 2 times or 1/2 times longer, but it's of course possible. So the main advantage of this paper is I'm not first author of it, but I believe that we showed that you can write simple probabilistic programs, and it works not worse and for simple problems than hard, long, bottom-up approaches and their implementations. And even with simple models, you have the same performance as bottom-up approaches. And the more complex you make the model, hopefully you will receive better results. And there is much to explore. Does this make sense?
Can you once again say where does the ABC come in? Because I cannot see you have a likelihood of how would you meet ABC computations.
So ABC really happens in this log likelihood. So each time we have our image, our new sample we have, where we make some small perturbation on our local variables, you either accept or reject your proposal, and it happens analogously to ABC, to MCMC ABC.
You have a likelihood in ABC, you usually don't have a likelihood, you only have some statistics you extract from your sample.
Yes, but in ABC the problem is that you cannot integrate over all possible explanations of latent variables of your provided real image. And the same thing we can do here.
Maybe we can discuss offline.
Yeah, I mean, yeah, of course. The main thing that you, yes. Okay, so there is thing which I also interested in, and I made contribution to last year for church-like languages. The problem was that in Church and MIT Church and Bears, the asymptotics of inference using Metropolis-Hassen algorithm was not the same as for handwritten sampler. So roughly speaking, when you increased your data linearly, the inference, which was necessary to converge to posterior number of inference steps, grows quadratically. Because if you remember the first thing I showed you about probabilistic programming, each time you make small perturbation, you reevaluate the whole program, and you rerun the whole program using all random choices whenever possible. But actually, if you have analogous notion of Markov blanket, you just should recalculate log likelihoods of direct children. This node depends. This node provides its values for, and you can accept or reject because all other values and their log likelihoods will not change. And this is what ventures and its data structures follows. And we have this analogous notion of Markov blanket, and hopefully paper in Nature will be published soon. So you will keep track of dependencies and just make the small perturbation and not reveal the whole program. And this allowed us to have the same asymptotics which you have for some real-world problems, for example, Ising, HMM, or LDA, to have the same asymptotics for that handwritten samplers have. Does this make sense, this part? Though, I mean, coefficients of constants are still very slow, and there is much work to do. For example, it's 1,000 times slower than handwritten sampler. And finally, I'm going to describe the preliminary work I have. If you don't have any questions on previous parts.
Finding the Markov blanket of a variable in an arbitrary program seems like quite a difficult task. Can you say something about?
I agree, because the thing you don't have fixed structure, and you should make walk to find your. You should do it online, based on your current structure. You should find all nodes which are structure influenced nodes, for example, predicates, until you can observe your propagation. Let's say if you have this node which you make local perturbation on, and if it's predicate node, you can't stop here. You should for example, delete SSHL and create another node if you go from consequent to alternate, if your predicate has changed its value from true to false. And we developed data structures which will be described in this paper. And the algorithm. Yeah, so I mean, it's the paper currently, there is a draft about 40 pages. And I mean, after the talk, I'm very glad to discuss it in person. But I mean, your intuition is totally right. That it's not Markov blanket as it is because we have flexible data structure. And we just should find all nodes which influence the structure up to nodes we can observe at, and then have this part as we make local perturbation on.
Isn't there another limitation that the node that you stop sampling at, you have to be able to compute the likelihood at that point, right?
Yes.
So if you have some black box like a renderer, you will have to sample through that, even in this scheme, right?
I agree. So
you can't really use the Markov blanket.
I agree. You're right. I mean, if, for example, this is not stochastic choice, but deterministic, for example, this is sinus function, you should propagate up to the node which can observe. Or, for example, this is edge case, and its log likelihood will be 0 if you feed a new value which has been produced by local kernel on your principal node. You as well should either do rejection, which will be very stupid rejection, because you will each time reject if it's an edge case, or you can propagate further. And all this will be described here, and I'm glad to discuss it after the talk. And by this, I want to show you that previous implementations of church language had not the best asymptotics you can have, but now it's better. Can I move for next section? So idea is to use church to have some method probabilistic program which will produce probabilistic programs, generative models. So you will make inference over probabilistic program space, and because church is Turing complete language, you can use eval to evaluate your programs you generated. So roughly speaking, if you have your inputs and outputs pairs, this is one of classical formulation of a problem. You want to come up with some programs. Sorry, this is error. It should be n, which from this inputs produces this outputs, and they are connected by some state. So in the simplest case, it's just the one program. It's more complex situation. It's programs which share the same parts, and so on. Does this make sense? And you can do it also in unsupervised way, where you have just outputs, and you want to find programs which generate these outputs. And this is one very stupid way, but just to see how it can work. So you just have some productions rules. Here you define somehow how you generate your program. So you have, then you wrap it using compound procedure. So you receive your sample, and you evaluate this expression. So you have received your sample you can sample from. And then imagine that you sample from this sampler 100 times, and you provide two arguments to this sampler, 5.7 and 3.5. And imagine that mean of this 100 samples is 5.7. And then standard deviation is 3.5, and kurtosis is 0.0, and skewness is 0.0. And then you either predict your expression, so you want to understand what program it was, or you want to predict 100 samples from this sampler, but using other coefficients. And the idea is you sample from your method generative model, then you apply sample generative models to train input-output pairs, and you make inference here using some inference algorithm. and then you hopefully converge into a reasonable generative model, which describes your input-output pairs. And the idea is to use currently PMCMC and MH to automatically produce classical distribution samplers like Marsagle or Boxmüller algorithm, because there is a much work on deterministic programs. There is field of functional inductive programming, of inductive logic programming, of program synthesis. But probabilistic programs are more general in the way that they have stochasticity generally, and it's interesting to see how in this framework you can generate and synthesize probabilistic programs which describe distributions and not some fixed algorithms. And for example, this is production rules written in Anglican or Venture. So for each combination type, you sample from some process. And for example, for real combinations, if your combination should return real value, you sample from some categorical, have some plus, minus, multiply, normal. If you have Boolean, you have Boolean operands. This is one way to describe the generative model.
You don't want to have normal in there if you're trying to create a Gaussian sampler, right?
Yes, but you mean that we should just have reals, right?
Well, otherwise the solution will presumably be just to call that.
Okay, but imagine that we have produced a model where we have if some predicate which returns Boolean, and consequent is some normal, and alternate is some other real. So roughly speaking, your combination, first one, which you want to have output value will be real, but this real could be if construction, condition construction, with predicate, which should be Boolean, and consequent alternative should be by recursion reals. In this case, you need Boolean, for example. Because idea is to have in prior all possible generative models. Does this make sense? Do you see?
Maybe we should take this question.
Okay. And this is Marsagle, written in Anglican Venture. And these are samples of generative models. So these are programs which has been produced by meta-probabilistic program. And these are distributions. So these are samples from sample generative models. And
what are they supposed to look like each other?
Sorry?
These four pictures, are they supposed to look like each other? Or
no. I mean, so roughly, they should be, in general, they should be different. Because in general, you want your program you generate from meta-probabilistic program be to define any distribution. Define normal distribution, gamma distribution, Poisson distribution, some processes. So
this is just four different distributions?
Yes.
Sample from the prior.
Samples from prior of your programs. So firstly, we sampled programs, and then we produced samples from programs you sampled from meta program. And the idea is to combine functional probabilistic programming with exchangeable random procedures and with different inference algorithms. You get benefits of using noise because it should allow to make smooth perturbations when you propose different programs or change parts of them. Parallelization and distributed inference techniques, and Bayesian non-parametric entry models to generate grammars, how to have smart priors on your programs. Okay, so I describe you very briefly what probabilistic programming is. As I see it, I described 2 examples. I described one thing you can advance, and asymptotics in church-like languages now is in correspondence for many models with handwritten samplers. And I also showed you ideas on automatic programming with probabilistic programming.
So we have time for a few questions.
So in your automatic programming project, how would you know if your prior over programs is a good prior? How would you even evaluate that?
I don't know yet. I don't know. I mean, the problem of prior is always a question. I don't know yet.
Okay. And also, one thing that seems weird with the way you defined it is that if I make a tiny change to a program, it could have a gigantic effect on the distribution produced by that program, right?
Could you repeat your question, please?
If I make a very small change to the syntax of a program, it can have a very large impact on the distribution of the samples generated by that program.
I agree.
So it seems like one of the difficulties, one of the issues you'd run into is trying to smooth out that space so that you can do a good, reasonably good search to that space of programs, right? Because if it's extremely rough, it would be very difficult to find a good program in that space, right?
I agree. Yeah, I mean, I agree with you.
Well, there are some changes that are more continuous, right?
That's what I'm thinking. Is there a way you could set up the problem so that when you change the program, you know that it will have a small effect on the output of the program, so that you're not just making arbitrarily syntactic changes to the program, as it sounds like you're doing, but some sort of more controlled changes to the program.
I mean, the way how, for example, if we follow the church inference algorithm, what will happen? You will have some operator, and if you have conditions, so if you have if flip one part of a program and another part of a program, if you make some perturbation on the construction of your program in the consequent branch, you will just touch this part. And let's say if the predicate sampled to be true 50 times, you will just affect half of your samples from this thing. So this is one way. And I agree that there's more to explore and to try ideas from program synthesis and program transformations, when exactly what they're doing, they're trying to transform programs with small changes to them.
So I guess another way to something from a program is more like, as you said, with program transformation. You could start with a very simple program and then apply a sequence of transformations from a grammar, similar to the work of Roger Gross and also some work going on here in Cambridge. And then in some sense, perhaps the steps that you can take are more carefully controlled.
I agree with you. For example, there is a paper by Professor Noel Goodman, Andreas Stulmer, and third author was published, I think, its technical report 1 year ago, where they're exactly trying to, firstly, they have observations, let's say 100 observations. Then they create exactly the program which creates these 100 observations. And so just using if constructions, roughly speaking, and then they make transformations on this program, as you described, roughly speaking. So, and they made it for one specific class of problems. And this automatic programming, it's just a proposal. I'm trying to explore this now. All this work is a paper. This is just a description of probabilistic programming. This is venture still paper in preparation, and this is just a proposal. And I hope it was helpful for you. I hope it was helpful for you.
So
So is there a way you could learn how much a program transformation would change the particular outputs? So, because if you had a minus sign at the top, it's probably going to do a lot. But if you put it somewhere down, very deep in the nested if, it's not. So, there's a way you could get some kind of feature that would give you a way of learning that to help you then smooth out your kind of search space.
I agree. I agree. This can work. I agree with you.
So you described the church venture Metropolis Hastings algorithm. One question I had was if each variable in the program is a big data structure, as in your automatic programming thing, how does it know what to propose for that variable? Like how does it propose changes to that variable?
You mean how it does local perturbation?
Yeah.
Currently it samples again from prior.
Oh.
Yeah, so I mean you can.
So not local.
Sorry?
So it's not a local perturbation.
I mean it's local perturbation, but it's sampled from its prior. So roughly speaking, I will show you. Imagine that you have this uniform discrete and size x. So, and imagine that this for size x for letter number 7, its size x was 17. You will make small local perturbation in the ways that for size x, you will just sample again from uniform discrete. And for example, will produce 55, and you will propagate it up to this render surface procedure, and then to stochastic comparison. So in this way, it's local perturbation, and you have some local kernel here, which in this case is just sampling from its prior. So, I mean, it could be another kernel. For example, you can sample based on your previous value. You can have another kernel. Not uniform.
Are there like commands to specify alternative kernels?
It's not, to the best of my knowledge, it's not yet described. So current venture samples from prior. And there is just work which is in the process where you will be able to specify. But on venture you can download. Now it's not possible to specify another proposal rather than just resampling from its prior.
I see. So, if no one else has a question, I want to ask another question.
Suppose you could sample a Boolean.
Sorry?
I suppose you could sample a Boolean and use it as a choice between the kernels, right?
Yes, I mean...
You mean set up the prior in a very particular way?
Yeah. So
Yeah, that was actually my next question.
The alternatives.
So because the inference algorithm works in this very particular way based on the structure of the program, it sounds like by rewriting the program into an equivalent one, you could have a significant effect on how efficient the inference is. Are you familiar with examples of that, or are there like certain programming practices that you should follow to make the inference more accurate in these programs?
Yes. There is not described as some tutorial, but now anybody, probabilistic programmer should, there's no tutorial yet, but your intuition is right. Currently, when you write any probabilistic program, depending on what inference algorithm you will use, you should think how inference will happen. Because, I mean, for example, I can provide you an example. Imagine that you have this node. If you put more attention to this, it's written in the way that it will jeopardize inference in church-like language. Because here we have categorical, but this categorical is not hidden. If you change your predicate, you'll just resample another categorical. And if you write your whole model in the way like this, even if you do your small local perturbation, even if trying to keep dependencies, making perturbation on this node will yield in reproposing all other nodes. because your predicate will change, you will go from consequent to alternate, and you will go up to bottom nodes. If you want to make it better, you should write categorical, and for first argument, if equal MVS to 0, 0.2, otherwise 0.3. And for second argument of categorical, if MVS equal to 0, you should specify 0.8, otherwise 0.7. In this case, it will observe. So, I mean, there are other tricks. For example, if you have if in your interpreter, in your engine, you can specify, okay, if I am switching from categorical to categorical, I still can try to observe. I mean, there is a trick, roughly speaking. But I agree with your intuition that when you write a probabilistic program, you should understand what happens, especially at the current stage where it's rough.
What about his suggestion that if I have a prior which is very broad, I write it as a sequence of steps that add noise, that add a little bit of noise at each step? Does that help the efficiency of the inference?
For some models, it should, yes. I mean, the problem with probabilistic programming now that there is just few algorithms really implemented, Metropolis Hastings and SMC and some other algorithm for another probabilistic programming language is not very familiar with, for example, infer.net. When you write a program, you should really have in mind how this algorithm works. And there is no tricks, for example, like this in current venture.
Okay. Well, let's thank Yura one more time.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.